let's start our third lecture on radio galaxies by Dr. Morganti. So, thank you, Raffaella.
I use this, doesn't matter. I use this one. Hi everybody, good afternoon. Thanks for being here. So I'm going to continue my talk, my presentation on Radio Galaxy, getting into something a bit more specific. So the first two lectures were one on the more technique instrument and technical way for radio. I put this somewhere on, should be somewhere, the PDF, and there is also a list of survey, radio survey, in case you want to have a look with the link in it. So it should be relatively straightforward to click and go. But let me know if you need more. And then not yesterday, Tuesday, I discussed a bit the radio AGN. So there were a couple of points, the mechanism, the morphology, and also the fact that you have always to be careful in separating radio from star formation. Something to keep in mind is not only AGN, and the different type of radio sources, including the one at very low luminosity that tend to have a certain type of morphology and some of the issue related. Okay, today I would like to move on and continue in a way on something that I started about the role of AGN and radio AGN in particular for galaxy evolution, let's say, and tell you about the life cycle of the evolution and life cycle. I mean, we have seen that jets are structures that expand, they grow, so clearly they evolve, and then they also die and restart. So this is what I want to discuss today. It's something quite unique that the radio AGN do, and much more difficult to find in optical AGN. Okay, so that's what I just say. So okay, so let me reiterate that the reason why I'm focusing on the life cycle and tomorrow on the impact on the gas is because the model, the simulation of galaxy formation and evolution really needs some extra action from either supernova or AGN. So here you see the two key correlation. We have seen also the other day that trigger the idea that there must be something connected, whatever happens in the nucleus, with whatever the galaxy does or will do. And so we have seen the clear correlation between the black hole mass and velocity dispersion in the bulge. So that's a structure on very, very different scale. So people are still trying to understand how come they are connected. And the luminosity function of and the luminosity function of radio of optical galaxy that without any extra component they don't manage the simulation and the theory don't manage to match the observation. The number of galaxy, either the low mass or the high mass, the simulation, if you don't do anything, they are completely off in their number. And so the solution for the small galaxy has been always from the beginning the effect of supernova, getting rid of the gas, stopping some of the limiting, let's say, the star formation. And for the high mass galaxy, the AGN is what is supposed to do the job, essentially limiting the star formation, so bringing down the number of big galaxy. So that's the key why we should care about AGN. By the way, we haven't really solved yet what is really the effect of AGN and whether it can fully do this job, but without anything in the simulation, this observation, these numbers cannot be reproduced. So yesterday, no, that is still not yesterday, but Tuesday. Anyway, yesterday for me, I show you the one of the simulation, just a part of this one, that is the Eagle simulation in this case. This is the structure formation from high redshift, so very close to the Big Bang, as the cosmic web forms, as the big structure form at the location of the node, and then as soon as the black hole mass is large enough, the energy start to be emitted as the AGN forms, and so start to be emitted. And as I mentioned before, there is an enormous amount of energy release, and so this energy, at least in this simulation, is released isotropically, and that's actually in the observation is not what is happening, but okay, these are very difficult simulations to do. And they are supposed to clear the galaxy from the gas or preventing the gas from cooling. This is a simulation, and what you see here is the temperature of the gas. So everything that is whitish is the hot, something shocks or wind, something that deviates from normal relaxed gas. And so, as I mentioned also the other day, you see recurrent kind of explosion. So, and this is what is telling you that in the life of a galaxy that is very long, the effect of the AGN has to repeat multiple times. If it doesn't repeat, then this accretion of gas that has to happen from the cosmic web will keep on going, and so more star formation than observed will happen. So essentially, recursively, you have to have this kind of explosion or something similar. Explosion, that's not the word, but okay. So in a nutshell, you can see the loop in a way that the supermassive black hole is growing because gas is accreting. We know that gas has to accrete from the cosmic web. The nuclear activity starts because there is gas that triggers this activity. But then, because the nuclear activity starts, that's the way in which the outflow happens. So gas gets ejected, may be ejected, something that we will see tomorrow, or the activity prevent more gas to accrete. In either ways, the idea, the final scope, is to quench the star formation. And then, but then because there is no more accretion, your black hole starve, if you want to. So it's not fuel anymore. So the activity stops, the cooling and the accretion restart, and then the loop starts again. This is really, in a nutshell, the idea of feedback. And this has to repeat multiple times. Okay, to let's say reproduce this kind of numbers. Okay, so now one of the questions could be, at least one of the questions that I have essentially every day, is why there should be this cycle. Okay, the accretion stop, maybe there are but that's really something very first order. The situation in itself is actually more complicated, and I cannot get into that, but there is an entire literature of people, of study, trying to understand how the activity starts, whether it's just via merger, I mean galaxy that come together and more gas comes, but that's merger not so common as that can explain everything, or just the so-called chaotic cold accretion, cloud of gas every now and then manage to end up in the close enough to the supermassive black hole to be used, accreted on it, or whether there are instability process in the accretion disk, the inner part where everything starts in a way. So there are various extra phenomena that can play a role and can make this feedback loop even more complicated. I just mentioned so for you to be aware. I don't want to I cannot get into this too much. Yeah. So these are simulation. This is a simulation from Gaspari et al. Of chaotic cold accretion, so that there is every now and then a cloud managed to leave some orbit and be and cool down and enter, because the problem is how the gas gets so close to the supermassive black hole. So these are simulation. This is a cartoon, but in fact it's connected to the simulation of Ciotti, bit older. So this is really, I put because a cartoon is always nice to have. And these are instead a result, again, from simulation, but of the more inner part. So why an AGN should last 10 to the 8. Okay, so that's the idea behind the story that I wanted to tell you today, and, well, actually, the one also of tomorrow. So, but what I want to concentrate is whether we see this loop of on and off activity in a radio AGN. And I hope to convince you that if you look at a radio AGN, you have a couple of diagnostics that you can use, in which you can say, this is a new AGN, this is a new phase of the radio AGN, this is an old one, this is a dead one. So that makes the very interesting for radio astronomer, if you care about radio AGN, to connect to the evolution. And I find this very exciting because actually the telescope that I told you about, a new telescope that I told you about on Monday, they have given us a lot of opportunity. So actually, we know that radio AGN, they have to go through on and off phases. We know because from the beginning of the study of the AGN, well, first of all, radio AGN lasts no more than 10 to the 8 years, and I'll get later to how do you derive this. So it's a very small fraction in the life of a galaxy. So if you assume that every massive elliptical goes through phases of radio, in which becomes a radio source, the fraction of massive elliptical that are detected in radio tells you, to first order, how long this on and off phase could last. So here you see some luminosity function of radio AGN. So this is the radio luminosity. So these are the big galaxy, the one that I showed you the other day, the Cygnus A of this world, really the nice one with the jet. As you go down, these are more the radio quiet that I told you. And if you look, this is in mass of the host galaxy. So the yellow one are the less massive, the dark one are the most massive. So essentially, if you go to high radio luminosity, the fraction of galaxies that are radio is relatively small. It's 10 to the -2, 10 to the -1 if you stay around this number. So let's say 10%. You will see very often in papers that you read this magic 10% of elliptical are radio AGN. Well, that's an average of all this complicated plot. But anyway, 10% means that 10% of the life of the galaxy will be spent in a radio, in a phase in which you detect radio emission. So this is how these people have interpret this radio luminosity function. So this gives you an idea, depending what kind of galaxy you have, you can guess, okay, this galaxy is going to stay most of its life as a radio source, this not really. But it's a statistical, I don't know. It's nice, but it's also nice to look into the eye of your object. At least I like it, but okay. Okay, so this is a statistical part. This instead is another argument for which people say, okay, a radio galaxy must be recurrent. So these are the X-ray cavity that I mentioned also on Tuesday. So these are actually X-ray observation, Chandra observation, very deep observation. This is why there is an handful of objects done at this depth. And what you see here, now better, is that the X-ray emission is not uniform, just, yeah. But there are all these deep, so-called cavity, where there is much less emission. So that's great. That was one of the findings of, I don't know, when was it? 15 years ago, something like that, when Chandra was still doing at his best. So the other thing is that everyone, or no, not everyone, but many of these cavities are actually filled with the radioplasma from the radio source. All this X-ray rich cluster have also a radio galaxy in the middle. These are so-called cool core cluster. And so what you see here is the blue is the X-ray, the red is the radio, and the radio nicely fill this cavity, but not all of them. So there are also ghost cavity, so-called, and then only by going very, very deep in a radio observation, in this ghost cavity, some radio emission could be found. So the idea here is that every cavity is one phase of activity of that radio source. So multiple cavity means that has been on, off, and you can derive actually the age of how long this cavity, how long it took to build this cavity. So this is telling you, it's quite a direct evidence, it's quite nice, that the radio AGN must have gone on and off. So this is the phase that is now on, but here there was a previous phase, and then in the meantime something went off and now on again. But these are, and actually, and will be clearer later, you can also derive the time associated to this cavity, both using the X-ray and using the radio, as I'm going to tell you in a moment. So you can start putting some age, like in this case, the largest part of the source, that is the green one, the radio source, is 200 million years, while the inner part is about 50 million years, plus or minus something, as you can imagine, but okay. And so you can start attaching some, okay, how long this activity has lasted. That is a very important number. It doesn't happen always in extragalactic astronomy to be able to do this. So, okay, this is great. This work on X-ray cavity has been really revolutionary, not just for radio galaxies, but in general for galaxy evolution. It's still probably the best signature of AGN feedback, I would say. But there are 10 objects, maybe a bit more, down so deep with Chandra that you can see the cavity. That's the problem. And Chandra is not getting better. You know, we are all getting old, including Chandra. So that's the problem. And so what I'm going to tell you instead is how you can associate the age of a radio source by using other properties, and in particular the radio spectral index. That is what we are doing, what people have been done for ages since the start of radio source, but now we can do even better. Okay, so, and we do this in order to have hundreds of objects, not just 10 or 15 cases. Actually, in the future, 1,000, million, whatever you can find. So to do real statistics. So okay. So I wanted to spend a few slides on the radio spectral index, because it's a quite a nice diagnostic if you can afford all the observation. So anyway, here is just an overview of what I have, what is our view of what is happening. And then at the end of the presentation, I will attach some numbers to this phase. So essentially, like in the AGN feedback loop that I mentioned at the beginning, also the radio source are supposed to go through this loop, as I have already anticipated. So there are newborn jet, where we really know that they are very small, not only very young, not only because they are very small, because the size could be misleading, because you have, with a radio jet, you have a beaming effect. I mean, a jet, as being an elongated structure, if you look at it in the wrong way, looks very small, but in fact it's just pointing toward you. But we have other ways, and I'm going to explain this in a moment, via the spectrum, to say, okay, this is a new radio jet. Then the source expands, as I've told you the other day, the jet grows up to a certain point, every jet is different, to let's say, adult kind of source. But then we know that the activity stops. We actually see this, and so that's interesting, because it matches what has been, what is predicted for the AGN feedback. And we also know that some radio sources restart. So this loop I'm going to explore mostly with spectral index. And these two phases here, the remnant and the restarted, are the really tricky one to observe, and to not only to observe, but to identify in the radio sky. So these are the tricky ones that now the community is concentrating on. These ones are relatively easy. So this part of the loop, okay. This one is the new things that is happening, but you need, because otherwise you don't close the loop. Otherwise you don't know how often, how fast they go through. Okay, so I put this a bit cryptic kind of plot, so I'm going to explain you this. I'm not going to repeat, but if you have questions, stop me anytime. Okay, so so what happens to a radio source is that when the radio source starts and is very small, very young, and I'm talking about parsec scale, a few tenths of parsec, that for extragalactic astronomy is really small. The radio emission tends to be like this, self-absorbed. So you have a part of the spectrum at high frequency that is thin, okay, then you get your power law that I've mentioned the other day, but you have a part that is optically thick, and so really there is absorption in your power law spectrum. So this kind of spectrum, combined with a small radio source, is telling you this source has to be young, has to be still embedded in whatever medium, has also provided fuel into your AGN, to your black hole. And interesting, the peak of where the absorption is present moves as the source grows. And we see this. We have radio sources of a few parsec, few tenths of parsec, few hundred of parsec, and this peak moves from gigahertz kind of frequency to megahertz kind of frequency. Bit painful to derive, but so you see the source becoming more optically thin as it grows. And indeed, large radio sources don't have this anymore, this absorption, but they have the power law, only the power law part of the spectrum. And then when, and I tell you that it's never a straight, nice, well-behaved power law. So I fooled you the other day, but it's as always something that actually tells you about the age of the electrons. So then if you switch off the source, so was the question? No. If you switch off the fueling, and so the production of the jet stops, this power law becomes even steeper because you don't replenish the electrons anymore. And let me explain what is happening here. Yeah, so essentially your electrons that are continually stream from the black hole in the jet that we have discussed on Tuesday, they emit, and so they lose energy. They lose energy in synchrotron emission, we have said, but also the adiabatic expansion of your radio source, inverse Compton, you can invent all the different mechanisms. But they lose energy in they emit energy again proportional to the magnetic field and the Lorentz factor of the electrons. So this means that higher frequency, because this higher Lorentz factor emits at higher frequency, radio frequency, at higher radio frequency your electrons, okay, no, there was an hiccup. Okay, your electron lose energy much faster than at low frequency. Yeah? Okay. So you have a situation of this. You have a nice power law, the one that I promised you on Tuesday, and the typical power law of an active radio source has a spectral index of minus 0.7. This is minus 0.8. This is quite classic, so it's something that maybe to remember. But then as time passes, so this is a log nu for the flux, so this is frequency, and this is the flux that you measure. As the time passes, the part at high frequency of your power law becomes steeper and steeper. And also, the break, so-called break frequency where this happens, move to lower and lower frequency. So the older your source is, the more steep is the spectrum at high frequency, and the break moves toward the low frequency. So you see here 3 examples. I have more in a moment. This, and then as time goes, this is the new spectrum that you measure. Of course, you need to have a multiple frequency to measure this. But if you really want to study this, you will find the TAC will give you time to do this. So, okay. So essentially, this is of course to first approximation because it depends also on the magnetic field. Let's forget about that for the moment. It's a nightmare for all of us, but okay. But this is to first order what is happening. And so this means that if you have the frequency of this break, you can derive, I'll skip the detail, but you can derive, with some assumption for the magnetic field, the time since the last acceleration of the electrons. So you can put a timestamp at your source. That's cool, I think. So, yeah, and this type of steep spectrum, they go from the minus 0.7 that you want, 0.8 that you find usually, to steeper than 1, 1.5, 2, depending. So really a difference in spectral index. Ha ha ha. Well, this is what I want to tell you at the end. So you will have to stay here until the end of my presentation. You cannot go. So, yeah. Well, this depends. I think I have some example later. Let me. I'll get back to you. This, for example. So this is a spectrum. So these are 100 megahertz. So this is, let's say, low FAR frequency. This is 1 gigahertz. That is the most common 1.4. Most common frequency that usually you observe, also because there are big survey on this frequency, and then you go to higher and higher frequency. So if you let this go, your spectrum will modify in this way as the time goes. At the time, I'll get back later. So, so you see, you have this break frequency that moves to lower and lower frequency, while the spectrum at low frequency, so this would be low far, stays relatively fixed for a longer time. So the low frequency are the one that takes longer to be modified. So what you observe there is can give you the age of very old sources, while at high frequency you lose immediately the flux. So you have to observe also for much longer to detect this object. And actually here I put some number and some frequency, but I'll get into the detail of this. But this is the 1.4, something like this. So as you can imagine, this is a quite I told you a nice story. There are a few complications like the magnetic field, but as a tool, it's quite powerful. So I have a short intermezzo of 2 slides, because all I've told you is okay, and is to first order, unless there are a reacceleration process. There could be shocks, there could be funny stuff, I don't know. Like the hotspot of these large sources are places where reacceleration happens. So there you get a complication. And I wanted to show you a couple of image, because I know some people work on clusters. So this is just to show you that it's not always so easy. This radio source can be really quite complicated, especially when you go in dense environment where they move around and they do funny things. So this is a radio source. The galaxy is here. There are jets at the beginning. You don't see here because the scale is too large. But there are also all these plumes around, because these sources in a group move around, there are bubbles, I don't know, it's very complicated. And if you look here you have the spectral index of this entire structure. I'm not sure you can read, but the 0.8 is here, is only in essentially in the source. This part corresponds to this part, and this is a nice 0.7, 0.8 spectral index, but all the rest, this structure are instead 1.4, 1.6, so much steeper. But there are structures in this big mass that have also a relatively normal spectral index. So in this structure, some other reacceleration happens because they are moving in the medium and there are shocks, interaction. And this is the case of a cluster, Abel 2255, where each of these mass is a radio source plus some diffuse emission, and this is the corresponding spectral index, where the blue is a normal spectral index of an active galaxy, and the red is a very steep one. So you see the mess in which you can get if you are in a complicated environment. So this was just to make my story a bit more realistic. That is not always super easy, but to first order, this is what. Yeah. So what you see in the. Oh, this is another galaxy that moves in this cluster. This is a dense cluster, and so has a funny shape also because there is a round pressure that bent the jet. So this is telling you that this galaxy is moving in the dense environment, and the dense environment can also produce, of course, shocks, and all this can impact the spectral index that you then measure. This is just to put a word of caution about how easy it could be to derive age from the spectral index. But I'm stay out of cluster, so that's I try to stay out of cluster. Okay, so okay, let me go back to what we do. So we are trying very hard, using, especially using LOFAR, but of course we need also something else. We need more than one frequency to find, dying, and restarted radio galaxy, because as I told you, these are the most rare and difficult to find. And then once we have found, to try to using the fraction of they are, using their property, attach some ages and see if we can fill that loop. So this is a LOFAR image. Well, I cheated because I put the two together, but okay. It's a prototype LOFAR image, but you will see something similar also if you look at 1.4 gigahertz. But you see here there are many radio sources. These are all radio sources. The majority are point-like, unresolved, but these are also interesting because they could be the young one. But many are unresolved by the resolution of LOFAR, but others are nice FR2, as we have seen the other day, nice stuff. Some are extremely faint. You see they have a diffuse emission, very, very low surface brightness. And this is what LOFAR is good in, detecting emission that is a low surface brightness and then could be the older part of the source, because it's been already fading away. So this kind of source, like this, are the one that we like most. The fainter, the better. Actually, here there is another one, probably. You see here, just to go back and how much fun is radio emission, some funny stuff on the screen is even better. Also here, these are all artifacts due to the effect of the calibration, limitation in the calibration due to the atmosphere. So it's not always all nice. There are some complications that. Okay, and so with this data, what we are trying to find is to identify this dying and restarted radio galaxy. The thing that we have new compared to people before us that did for many, many, many years is that now there are this survey with a very large field of view. So one pointing of LOFAR is 25 square degrees. So you have, a large area where even if these objects are rare, there must be some of them in it. Easy, in a short time, you can just spot them. And then we have the spectral properties, because this is our LOFAR point, but then we can combine with some of the survey like NVSS that we have at 1.4 gigahertz, and the morphology. So, okay, so that actually is the work that some of the students that I've supervised, they have done. You really need a good PhD student to do this work. They are patient, they are dedicated, wonderful. That's really, and I just put here, just for fun, the cover of their thesis. So this is Marisa Brienta that she finished in 2017, I don't know. And this is Nika that finished not so long ago, last year. So the Dutch theses are this book with a collection of their papers or their article or whatever, but also they can really get very creative in their cover of the page. So it's very nice books. So collectible almost. Yeah. Yeah. Okay, that was just. So what we do, we take an image. This is again a LOFAR image where you don't see anything because it's too big, and so it's difficult to. But you see there are some radio source extended, the giant one, some radio source. So I have expanded here, and no, the student, because I have done not that much in this, but okay. You first have to, let's say, identify all the sources that you have. In this case, it's about 5,000 for this, and then select based on their properties, so that we could extract what they could be remnant, dying sources, or restarted radio sources, to count them. what we do, what we have done, in all these 5,000 radio sources, we take out the compact because we cannot say much about their structure. And for the other, we go and look which one they could be candidated dying sources. So they don't have the core anymore, they don't have a hotspot anymore, they are just amorphous kind of structure. Very faint and very amorphous. So Nika had a lot of fun selecting these sources. So these are some of the radio sources that we call as dying sources. You see, they are very different from the one that I show you on Tuesday. They are, and so because the LOFAR can go to this low surface brightness, is very sensitive to that. That allows us to detect them, and also to detect and to see that in their morphology there is nothing that could correspond to active structures. And so we have found that about 10% of the radio sources are dying sources. If you have a sample of radio galaxy, 10% are in this state. But actually, a radio source in itself is a pretty useless kind of thing, because as soon as you want to characterize it, you need the redshift of the host galaxy. You need something else. That's a limitation of having radio sources. So these are example of remnant radio sources selected by Nika and Marisa. Yeah, poor resolution kind of, where the contours in this case are from the radio, and the underline is the optical image. So the painful job then is to identify which optical galaxy could be the host of your radio. So the one that has the black hole that originally had the jet that built this structure and then stopped. So this is quite a time-consuming job. This is another example where an easy one. The red was the diffuse emission from LOFAR, and bang, in the middle there is this big elliptical galaxy. So we have decided that this was the one that has, in the past, created this emission, but then it stopped. There is nothing active in this. The electrons are not sent anymore. Let's say there is no jet, and everything has stopped, and slowly this emission will fade away. So this is something that is a time-consuming job, except for cases like this that, as you see, doesn't always happen. But you need this, and then the redshift usually are photometric redshift that actually the LOFAR, some of the LOFAR data release as added product. And so among the various objects, I wanted to show you a real a case. How do we do then? So this is what we have called a remnant source. So compared to the other, this is an old LOFAR image, not very nice. But anyway, we spotted this. That is this remnant amorphous structure, and this is the spectrum of this thing. So the LOFAR, you see the different telescope that we've used and the different frequency that we have covered. So LOFAR, okay, Vance is low frequency, all the low frequency survey from Westerbork, more recent, dedicated. And then you see when you go to high frequency, then becomes difficult to find telescope that actually, or survey that actually are deep enough. But using this is an integrated spectrum of this thing. So every point is a different frequency, the flux of this structure, very high in LOFAR and then going down and down. And these numbers that you see here are the corresponding spectral index between this frequency. So it's quite flat, this is what we call flat at the beginning, and then gets steeper and steeper as you go to higher frequency. And using this, you can derive the time that this source has been on. In this particular case, because we had many points, 15 million years, and the time that has been off, 60 million years. You can do by fitting this broken, so-called broken power law, because it's not power law anymore. So in this case, you know that the on and off cycle is about 20%. It's 20% of the time is on and then goes off and so on. Yeah, you cannot do in every object, but if you have enough point, this is what you can do. And you can do essentially just by using this formula that I told you before, making some assumption about the magnetic field and deriving the cooling time, essentially, the cooling time of the electron that have brought this break at the frequency that you observe. This is actually another object, but it was just to show you in practice how you do. The magnetic field is a question mark, as you can imagine. It's something that is not easy to, and is an art on itself to try to derive from different, but I spare you this, because, okay. So far I've shown you many of these so-called integrated spectral index. So you take the source, you add up all the flux, and you put a point in your plot, like here. But actually we are getting to the point that you can even make an image of the spectral index. So you take two images, one LOFAR at 150 megahertz, for example, one at a higher frequency, 1.4 gigahertz, whatever you have. And this is why the list of survey that I gave you can be so important, because there is, if you don't want to do new observation, there is where you go. And then you can combine these two image and create the spectral index that give you the flux, the corresponding flux that you measure at these two frequencies. So you can create a spectral index image that show you how steep or not the spectral index is. In this case, for example, very steep, 1.8, all throughout a source that is few hundred kiloparsec in this case. So you know that the entire source has to be a remnant and dying, is the leftover of an active one that now is just in the process of diffusing away. So you can do this, and you can start finding some interesting ages, the limited ages, the ones that are really the older one that you see before they disappear, at least at the sensitivity of the observation that we have right now. So we get to ages of 160, yeah, between 150 and 300. These are the oldest radio remnants, so not active anymore, but just a leftover that we can measure. Over, as I say, they can be, now they look like they don't have much structure because we don't have the resolution, spatial resolution, but these are very big sources. Okay, so in this work there is a lot. So because LOFAR and also the low frequency instrument in Australia, that is the pathfinder for SK, have opened up this possibility to connect really to measure also at low frequency this structure. There is a lot on the modeling of the source. There are many groups now doing more sophisticated modeling. And yeah, I don't want to give you all the detail, but if somebody is interested can always come to me and ask. But you can count how many remnants you find, or dying radio source you have, compared to the ones that are active, and make this kind of histogram, where the green one are these are the result of mock catalog that you can make by assuming that your source switch off after a certain time and then expands adiabatically expands and slowly lose emission. And take into account your sensitivity, because of course if you will be 10 times more sensitive, you will probably manage to follow the source longer. So you have to take into account how sensitive your instrument is. And the result of this mock catalog give you a distribution of ages of the source, active and dying, in an hypothetical sample. So what you see here is the distribution of ages from this mock catalog that reproduce our observation with LOFAR. And so the green one are the active sources, and as you see, they go from 10 to the 6 or a few times 10 to the 5. These million years, these are the very young radio sources. These are radio sources that are at most a kiloparsec in size inside that area. They have typically age of a million years. Then you have all your, let's say, adult radio sources, and then the brownish one are dying sources, so where we in this mock catalog have switched off the activity, and some are just switch off, are the light brown, and some are the oldest one that are still visible in our observation. So you see here a bit the range in ages that you reach. So you have around 10 to the 7, few times 10 to the 7 is when typically a radio source lasts, is how long it can last with activity, and then typically gets switched off, but then can go on until 10 to the 8 years as visible, at least in our sample. So in this way you start building this age. Now I really need to speed up, but I wanted to mention that now we have also, so the remnant in a way are now have entered the classification of relatively easy to spot. So we have made progress. Before they were really rare. Now we have a machinery to find them. Not only we, there is an entire community out there doing. But the restarted, that's the tricky one, because otherwise you don't close the loop. So there are restarted radio galaxy, and we know since a long time that there must be. The most likely one are this so-called double-double. It's not a nice name, but this is what they are called. So you see they have, this is, actually this is a triple, but okay, doesn't matter. Let's look at this in the middle. So this radio source have 2 lobes, larger lobes, and then in the inner part they have other 2 lobes. So it looks like they are repeatedly have a phase of activity, one, the other, with some break in between. People have tried to simulate this and fail all the time. So this will be your first jet that then stops, and then a new one starts. And no simulation managed to actually reproduce the morphology yet, because they seem easy, but they are far too complicated. But so these were the signature of restarted radio source until not so long ago. There are more sources, not all so nice and elongated, that we know they must be restarted. This is an example. So you see a big blobby source, very amorphous, the large part. But in the middle, there are 2 tiny lobes, about 1 kiloparsec, with that has a spectrum, a peak spectrum, peak around a megahertz. So this looks like a restarted object. Okay, and so using the same idea as for the remnant, we have started selecting the candidate restarted radio source. I don't give you all the detail, but what I want to mention is that the double radio galaxies are really just a minority. They are really special objects in the sky. So they don't tell us the entire story of how often how often restarted source are in the survey. But so we end up with about 15% of our sample of radio sources having some restarted radio galaxy in it. And so, again, this is an important number that has been quite painful to extract, but there is a lot of work behind. But again, ask if you are interested. But it is important because, again, it's telling you how often this activity must have started again. And so, if this 15% is correct, the restarted activity happens relatively often in radio galaxy, more often than expected. And so the modeling of radio galaxy and the life, and also the impact, must take this into account. We also have some nice example using the resolved spectral index of objects that are that have two different type of spectral index inside the same radio emission. Maybe this is the clearest one. There are lobes with spectral index normal, surrounding by emission of very steep spectral index. So something that only the spectral index can tell you that a restarted phase has happened. These are very old electrons. These are the new one. So we can do this now systematically for many, many hundred sources. So, putting all together with few corners that I cut, but okay. This is a bit of this is the same loop that I showed you at the beginning, but with some numbers attached to it. To just give you an idea of the progress that we have made in trying to quantify the life cycle of these sources. So as I mentioned, young radio sources are typically, they are the ones that really are embedded in the very inner part of the galaxy, the denser one. And so typically it's 1 kiloparsec, something like that. And it's the 10 to the 6th year. Then the jet breaks out from this denser part, and you will see tomorrow also what is the difference in this part. And then the source stays in active phase for 10 to the 7, 10 to the 8, it depends. And then we have the remnant phase following when the activities switch off, and a restarted phases that can happen after a few tenths of million years, derived by some of the spectral index analysis that we have done. Always with this trick to associate the curvature with the age. So this is, but you see I put also some deviating paths, because the life is always complicated. There are galaxies that die young, and you can see, so there is actually a range in ages. Not all the radio galaxies last for the same number of years or million years. There is a range, and it's still unclear why a radio source has to die when it's only 10 to the 6 or 10 to the 7 years. So probably instability in the disk are the most likely candidate to destroy the jet, essentially. You create either magnetically or just for instability, you destroy the jet. That is, after all, a kind of fragile structure. So this is, I think, this is, at least for me, quite a step forward, because this kind of numbers were not attached to the life of the radio source before, and also the fraction of restarted and remnant were not known. So now these numbers are becoming more and more solid, because more groups are working on this and so on. Of course, we have looked so far only at a certain group of galaxies, so we are still biased. We will see how biased these results are when we go, for example, to fainter or less massive host galaxy, for example. But okay, I'll skip this, and this is actually my last slide. So why I bother you for 1 hour about this? Well, first of all, I'm very proud that we are starting putting this number and ages together, because this is something quite unique. I mean, you don't work on only a small fraction of you works on extragalactic, but attaching ages to the activity is something that, yeah, many people are fighting with and trying to be very creative with. So with the radio AGN we can now do, and it's very interesting. But actually the main reason why I'm telling you this, going back to the beginning of this lesson, is that if you identify both the young but also the restarted radio source, we actually have seen that these phases are the ones that have more impact in the gas in the galaxy. So when a jet starts is when it does most of the damage to the surrounding medium. And when it restarted, is the same, is again impacting the medium around it. And this is exactly what the feedback needs, or the prediction for the feedback are. You need to have the AGN doing something. And what we find now is that the young, in these phases, they do most of the damage. So it's quite important to know when a radio source, in this case, is in this phase, and how often it is in this phase. So this is why we are doing all this, to connect to the gas. And so the connection to the gas is what I'm going to tell you tomorrow. Thank you.
Raffaella, thank you. Questions? Sorry. Questions? We start. Questions?
Hi, Raffaella. So I wasn't. This only happens on elliptical galaxies, or a small percentage of?
Well, yeah. So the last part, the part that we are doing with the LOFAR data is, I would say, mostly on elliptical galaxy, because we have to make some selection in the type of sources that we can study.
And so,
But there are examples of but then so no, let me start again. What I told you, because it's also the newer thing that is coming online, is the statistical part, in which we study samples. We can do statistics. We can say 10%, 7%, 15%. But then there are plenty of single object study, where also lower luminosity radio source shows this loop, the restarting. Like for example, this one that I show you, this object over here. This is a low luminosity radio galaxy, a radio quiet almost. So I think this scenario can be expanded. Whether the numbers, the fraction, the time scale we hold, that's I don't know yet.
and so when not trying to get any spoilers for tomorrow, when I mean the feedback, you mean in the past? I mean, since they are restarted, I mean.
Well, no, it's the new jet. It's the new
Okay.
jet that restart. So you have the old one. Okay, it's all done. But the new one, every time that inject.
This could
Yeah,
initiate a new star
yeah,
formation.
yeah, and then
Okay.
reinitiate
Okay.
outflow,
All right.
especially. This is what we are looking for.
Cool.
Yeah.
Please.
Please, can you show your picture of the low far where you have a lot of jets with bubbles, with
Yeah,
lobes?
This
Yeah.
this one.
It doesn't change.
Oh, oops. Oh no, disconnected. Because I'm disconnected. So, but didn't say that. Because it doesn't say here. No. Yeah. Okay. Maybe here. Okay. I killed him. How do I kill this?
Here.
The other side. Okay.
And your presentation should be here. Okay. And then goes to here. And there. And modo actually.
Whoa. We are organized. Okay.
This one.
This one.
Yeah. Apparently, there are a lot of. Visually, there are a lot of jets, and
Yeah.
and you and your collaborators can find more than those objects that visually can be detected. So, two questions. All of these events happens in elliptic galaxies?
Well,
And my second question is, in this field of view, how many elliptic galaxies there are? So it seems that for each elliptic galaxy there is a jet with lobes.
well, if you go deep enough, almost for every elliptical there is something, some radio detection. Not necessarily a jet, big jet, but that's the idea. That was the statistic that was in the other plot. So if you have a massive enough elliptical and you go deep enough in radio, almost every elliptical has some radio emission from AGN. Not star from AGN. So that's correct. In this particular case, life is too short for doing everything. So the selection was done. We mostly concentrated on extended sources because then we could see the morphology, we could study the spectral index resolve. So there are a few things that I didn't mention. And then if you take the resolve one, the large majority are elliptical of the one that we have studied. Yeah, this is what I was saying, yeah. So the fraction of spiral that have a larger radio jet is small. It's not zero, but it's small. At this resolution, of course, if you go, even if they have some radio, it's small. So most of this kind of object, like this or like that, they will be associated to early type. Yeah.
Thank you very much.
More questions? Because I have some. First, let's stay here. So, do you have an optical counterpart of this same field?
Yeah, this is a Lockman-Hall field. That is one of the famous fields. We started with the famous one because they have a lot of ancillary data. And actually there is some of the low-far field, not only the famous one, have all public ancillary data and identification and photometric redshift. So we build on the shoulder of well, it's a lot of work. It's really a lot of work to do this.
Okay,
So in this case, it's the famous field.
Okay, for that reason, you say that usually all these radio sources are associated to an elliptical galaxy.
Yeah, because
of the
we have
optical
done
match.
we have done, and other people have done. Yeah, at this level, at the level in which we can do now, that is already a step compared to before. Most of the cases are elliptical.
And now, there is a relationship between the jet the jet power and the black hole mass?
Oh. The jet luminosity, the radio luminosity seems to correlate less with the black hole mass than with the stellar mass. So that is maybe, yeah, no, I'm going the wrong direction. That is also something that people did not expect, but that's in detail. If you go, okay, no, I won't manage to get. But the strong correlation in the fraction of radio and radio luminosity is with the stellar mass. The black hole mass seems to be less correlated. The black hole spin could be really the crux of, but to know the black hole spin, we are not there yet.
Because my next question is related to that, in the sense of, let's suppose that you observing radio with LOFAR and you see a point-like source. So you may say, apparently, oh, this is a young source.
Mhm.
This is a young source because I don't see any dying radio emission.
No, this I will never say.
Oh, okay. No. I mean, I extracted from
Yeah,
that,
okay,
like.
okay.
But what can I have? So I can assume that. I can't assume that if I see a radio source that is just point-like and is not extended, it's just a newborn. Is a
No,
newborn
no,
or is a
no,
restarter?
no.
How do I differentiate?
No. One thing that I haven't discussed at all in this in the 3 lecture is the fact that there are beaming effects. So all the quasar, for example, the quasar that have radio emission, most of the quasar are small source because the jet is pointed toward you. Because the jet is like the broadline region. You know, you have the accretion disk and then you have the broadline region, and if it points toward you, you see the broadline region and you see also the jet in the same direction. And so that shortens your radio source. So your radio source becomes a small radio source. This is why only the size is not enough. Then, if it is small, it's also self-absorbed because it's in the middle of the galaxy, and that affects the radio spectrum. So you need these two, at least these two. Forget about the BLBI, that is another.
Okay, thank you. More questions? If not, let's go into thanks, Raffaella, again.
Thank you.